String seminar. We are very happy to have Rajath Radhakrishnan from ICTP. Tell us about reconstructing age group from extended operators.
Yeah. Thank you for the introduction and thank you for the opportunity to speak. So I would like to talk about certain extended operators in generic gauge theories, which would be line operators and surface operators, and study what properties of the gauge group is encoded in those operators and their properties, like fusion rules or OPEs. So because I'll be dealing with topological lines and topological surface operators, many of these things can be said or rephrased in the language of higher form symmetries or non-mutable symmetries, if you are more familiar with that language. So I've just written down a table of 0 form and 1 form, which will be the main ones that we'll deal with, in 2D and 3D, which will be the most of the examples that we will be dealing with. So 0 form symmetry in 2D is they are implemented by lines, and in 3D they are implemented by surfaces. And 1 form symmetries are implemented by point operators in 2D and lines in 3D. So lines, surfaces are the two kinds of topological operators that we will deal with in this talk. And depending on the dimension, they may be implementing 0 form symmetry or 1 form symmetry. So that's just something to have in mind. So the main point is, that's not working. Yeah, okay, thanks. So the choice of the gauge group constrains the structure of the gauge theory that we have. To give some examples, we have Wilson lines in a gauge theory, and the question of whether they are labeled by rational numbers or real numbers is a question about whether the gauge group is U1 or the real numbers. So that's one way. So if we, instead of choosing the gauge group, suppose we had the spectrum of line operators, then we can ask, what is the gauge group? And that question can be answered if we know the charges of the Wilson lines. If we know that they're only rational instead of real numbers, we know about the global structure of the gauge group. Another example is in the context of gauge theories, where we can choose a Lie algebra, but the choice of the global form of the gauge group depends again on the charges of electric, magnetic, and ionic line operators that we have. Example is, suppose we choose SU2 Lie algebra, then we have the global form to be SU2 if the charges are of this type. If we have the global form SO3 if the charges are of this type, and then many more examples of this sort. So once we know the Lie algebra, suppose we know the Lie algebra, to fix the global structure of the gauge group, we need to figure out what is the kernel. So what is the abelian group K, which lives in the center of the universal cover? That we need to fix this K and the Lie algebra to fix the global structure of the gauge group. So if we know the Lie algebra fixing the global structure of the gauge group, we need an abelian group worth of data from some properties of the theory. So if we know the line operators in the theory, then we can use the charges of those line operators to fix this K. Then we know the full structure of the gauge group. So this talk would be about like a finite group version of this. This is G, a Lie group so far. Now we can ask this question for a finite group. Suppose we have a gauge theory, which is a finite gauge theory, where G is a finite group. Then we don't have a Lie algebra. Everything to fix is this K, which is now a non-abelian gauge group generically. And the question is, what properties of the line operators or surface operators, etc., membrane operators, we can consider all kinds of operators in the theory. What properties of the operators tell us about the finite gauge group? That is the main question. Any questions at this point?
Has it been done for infinite? I mean, has it been done from Lie groups? What you're saying?
Yeah, I think for Lie groups, it's known in the sense that if we assume the Lie algebra, then we know how to fix K by looking at different charges. But if we don't know the Lie algebra, then there's a question about, can we know about the Lie algebra from different aspects of the gauge theory? And that is a lot more data if we don't know the Lie algebra. But assuming that we know the Lie algebra, then we just have to fix this abelian group K, and that we know.
Okay.
So I think for SUN, SON, all of those groups, this paper considers all of those cases and tells us how to find the K. So, so what is the motivation to do this for finite Gies theories? So one motivation is to really look at bootstrapped QFT. So if we have a lot of symmetries in the QFT, like let's take the case of topological QFTs, where we can use the topological symmetry to really constrain a lot of properties of the theory. In many cases, we can solve them depending on the dimension that we are in. And we can write down the theory at the level of the spectrum of operators, the correlation functions, etc. Given that data, the question is there a Gauge theory description of that bootstrapped QFT? If there is, what are the different types of Gauge theory description? Because Gauge theory description is not unique. So given a bootstrap data, for example, for 2 plus 1 dt QFT, we could call it the Moore-Seiberg data or the modular tensor category. So that is the abstract way of writing down the set of line operators in the 3D TQFT and the correlation functions. Given that data, do we know whether that theory admits some kind of Gauge theory description? So that's the question. So that's the motivation, and we will try to do these in explicit examples as we go along. Another motivation is gauging. So here I will just have to give some example where we look at two-dimensional theories. So suppose we have a 2D CFT with abelian G symmetry. So this is a 2D CFT with abelian G symmetry. Suppose we orbifold it or gauge it. Then we get, so suppose I call this CFT C, and I call this CFT after gauging G, C mod G. So I'm assuming that this G doesn't have any anomaly. We can gauge it. We get some CFT C mod G. This theory has a quantum symmetry, as it is sometimes called, or dual symmetry. G hat. So I think this by Waffa. So when we orbifold a CFT with a discrete abelian symmetry, we get a CFT with a dual symmetry, G hat. And if we orbifold this CFT by the G hat, we go back to the original theory. So G hat is dual in the sense that we can gauge G hat of this new CFT and go back to the original theory. So this is the case for abelian groups, and G hat here is actually isomorphic to G. They are acting on different theories, so we have G hat notation for it. But we can generalize the story even when the group G is not abelian. So suppose the group G is not abelian, then G hat, we will replace it by another name. We will just call it rep G. And rep G will stand for all the irreducible representations of the group, and the multiplication on that set is given by tensor product of irreducible representations. So rep G is not a group anymore for non-abelian group, it's a ring. So the dual symmetry that we get is actually a ring, not a group. And there is a notion of gauging this dual symmetry to go back to the original CFT with the group like non-abelian symmetry G. So this story generalizes to non-abelian G, but we have to deal with these non-group like objects. But there is still a notion of dual because we can gauge this and go back to the original theory. So in this scenario, one of the motivations comes in this scenario where the structure of G, which is just the group multiplication of G, completely fixes rep G as a ring. We can find the ring structure, the multiplication of the ring rep G starting from G. But suppose someone hands you rep G as a ring, we cannot fix G as a group. We will see some examples. So there are examples of groups for which rep G is the same, two distinct groups. So we cannot fix the group from rep G. So the question is, what extra data do we need to fix the group? So that's another motivation. Yeah.
Are you talking about continuous groups right now or general?
Just finite groups now. Yeah, just finite groups. Because I'll be dealing with, I would like to use properties of topological operators. And for finite, if I choose finite groups, I guarantee that the operators that appear are topological. If I go to Lie groups, then I have to take care of other complications. It won't be, the OP because these are not topological operators for Lie groups, the OP will have some dependence on the position, so I have to be more careful. But here I will deal with just finite groups. Yeah.
Also, suppose I fix a group G and I change my theory. So ref G will change, the C in the C mod after this quotienting.
So if I take a different theory here, and if I have the same G, I have the same G as a group, but the action will be different, right? So the dual group will still be rep G. It is determined by G completely. The action of rep G on this new theory will change. So as an abstract group and an abstract rep G, this completely fixes rep G as a ring, but rep G as a ring doesn't fix G.
Could you clarify then what do you mean? Like, how do you define rep G independent of this C? Like it's just an algebraic thing, right?
Yeah, it's just an algebraic thing. So I can, so let me write down rep G. So suppose, so we start with irreps of G. So some R1, R2, etc. Some finite list because we have a finite group. Then the ring structure is just given by tensor product. And we have some decomposition into some Ri. So this is the ring structure of rep G. And this I can define for any group, right? We can start with a group and define this. But this structure is not, the structure doesn't fix the group that we started with.
How does putting a CFT and demanding a symmetry by a non-abelian group G and then quotienting it and figuring out rep G help you in determining G? How will that help?
Yeah, so here I was just, so I'm not going to gauge the symmetry in this talk. Here I just gave the scenario because rep G is thought of as a dual symmetry. So they should be in the same footing, but at least at the level of multiplication on this structure and ring on this structure, they are not on the same footing. I just want to highlight that. Then I will describe what I mean by adding more data here to get G back.
Sure.
Yeah. Okay. So another motivation is doing like physical mathematics for finite groups. So we will see that the question of determining group from line operators is closely related to determining group from the character table, which is something that mathematicians really care about. And we will see that when we extend this to include other operators, it will be a generalization of that mathematical question to certain representations that we will study. So it is also interesting from the level of learning about groups from representation theory data. So this is some of the motivation. So this is a plan. Plan is we start with Wilson lines in a gauge theory, describe some properties of Wilson lines, and talk about what we mean by getting G from Wilson lines. Then I will talk about certain surface operators in a gauge theory, and then talk about the relationship between surface operators and certain representations called higher representations. And then I will describe what I mean by getting G from surface operators. And then we will also describe gauge groups which actually have isomorphic surface operator fusion. So this will be an interesting example, and then I will conclude. So this is the plan. So let me start with Wilson lines in gauge theory. So let me go back to Lie group just to write down this explicit expression here, and then just note that when we deform the loop C, so we have a loop C and some integer alpha, which we're using to define this Wilson line. If we deform the loop, so we have C1 and we deform it to C2, then the Wilson line generically changes. And the compensating factor depends on the surface that we have, depending on dA. Now I just wrote it down here because this shows that Wilson lines for Lie groups are not topological. When we deform the loop, we change the operator that we have. But for finite groups, dA is 0 for any gauge field. So there is no compensating factor if we deform the loop. So for finite groups, all Wilson lines are topological operators, and their OPE will not depend on the distance between the operators or any position dependent data.
define that object. An explicit definition.
Yeah.
Of a Wilson line. A finite group. I guess I understand it in the language of Z2 gauge theories, where there is a discrete gauge group. So we can actually form Wilson lines essentially by product of Z2 links.
That's right. Yeah.
Is that what you have in mind? But
yeah. So for cyclic groups, we can just think of it as taking the U1 gauge field and putting a different holonomy constraint so that we get some discrete. We can embed it in U1. But for more general groups, we will have to use the mathematical language will be different from this.
okay, so let me just continue my question, because so if you talk of a gauge theory of a discrete gauge group, let's say for Z2 it is simple, for Zn it's simple, but you have an arbitrary discrete group. Then suppose I have a square lattice, then are you saying that the links essentially are elements of the group?
That's right.
That's how you define the gauge theory, and then basically you will sum over all possible values of the gauge group. You know, just the way we do it for lattice gauge theories.
That's precisely the way in which I'm saying. Yeah, we triangulate the manifold, put the group elements along the edges, we sum over it. Yeah. So for finite groups, because these gauge fields are flat, there's no dependence on the exact shape of the loop. So these are topological line operators. And because these are topological line operators, they implement different kinds of symmetries depending on which dimension we are in. The 2 dimensions, a 0-form symmetry, and 3 dimensions, we'll have 1-form symmetries implemented by Wilson lines. So, what do I mean by G from Wilson lines? So I mean in the sense that suppose we know the OPE for Wilson lines. So we have 2 Wilson lines labeled by 2 irreducible representations, R1 and R2. We can bring them together and define the OPE for a Wilson line, which is, we can write this fusion of Wilson lines as a sum over some Wilson lines with some coefficients here, some integer coefficients here. This sum is exactly the same as, so when we fuse these 2 Wilson lines, we just multiply the charges R1 times R2, then we can decompose that Wilson line into a sum of Wilson lines over irreducible representations again. So this fusion of Wilson line is the same as taking tensor product of representations and its decomposition. And this integer, we know we can fix from the character table. So if we know the characters, we can just write down a Verlinde type formula for the coefficients using the characters. Also, if we, so before that, so Wilson lines along with the structure, this multiplication forms a ring rep G. So we will call this structure rep G involving Wilson lines and this multiplication. Now, eigenvalues, so suppose we know these integers, we can find the eigenvalues of these matrices. So this is a matrix, if we fix R1, for example, it's a matrix with rows and columns labeled by R2, R3, we can find eigenvalues of those matrices and recover the character table. So this is a two-way street. We start from here, we can recover this. We can start from here, we can get this. So the information in these integers and the character table is the same. We can go between them. So another way of saying is, trying to figure out what the gauge group is from the OPE of Wilson lines is the same question as figuring out what the group is from the character table. So if I give you the character table of finite group, what is the group? And this is the very, it's a major question of interest in group theory community. Even Brouwer in 1963, he defined this as what is the different properties of the group that can be found from character table. It's an interesting question. Yeah.
I have a question. I mean, one way it's obvious, but is it obvious that, I mean, it must be quite, it's some theorem, right?
It's a theorem, yeah. That's right, yeah. So we have to find so one way to do it would be to kind of come up with a basis on which a set of eigenvectors, somehow cook up a set of eigenvectors on which you act with these matrices and characters comes out somehow. So there's a construction you can do. Yeah, I'm not claiming that this is trivial. Yeah, yeah. No, I agree that this requires some steps. Yeah.
Hello.
Yes, hi.
Can I ask a question? So The point is that, if I give you a set of representations, and if I give you all these Clebsch-Gordon coefficients, then, how many, conjugacy classes are there. Okay. And I guess you can give the class function on that, which is what you mean by character table. But at least I'm not seeing how will you know, for example, in any conjugacy class, how many group elements are there? Even the cardinality of the group, how do you get from just a Clebsch-Gordon coefficients?
Yeah, I will come to the order of the group and conjugacy classes in just a few slides. Yeah.
Okay, fine. Okay. So but I'm just trying to understand, when you say you can construct the character table, are you just meaning that, you just know chi at, you know that there are so many conjugacy classes and you know the class function there, and the character as a class function there, or are you're actually saying that you know how many things are there within each conjugacy class and so on?
Yeah, when I say a character table, I mean there's an abstract set of rows and labels for rows and columns, and you just know that matrix.
Yeah, but the rows and columns are elements of G, or are just the classes?
Just the classes, just the classes.
Okay. Okay.
Yeah. Yeah. So so before going more in depth into what kind of properties of group can be determined from the character table, let me actually go through an explicit example and try to say what I mean by constructing group from bootstrapped TQFTs or QFTs. So in this case, I will deal with abelian TQFTs because they have a very simple description. So a 2 plus 1D TQFT, and I'll assume that there are no local operators. So you can have Chern-Simons theory in your mind, or 2 plus 1D Dirac-Witten theories. So they are completely determined by a set of line operators that we have in the theory, OPE or fusion rules of these line operators. And third one is actually the most difficult, but I can say it just as correlation functions of arbitrary combination of line operators, which is the hardest thing to kind of determine. Even if we give these two, it's hard to determine this. But for abelian TQFTs, which I will define now, this simplifies drastically. So what I mean by an abelian TQFT is that the line operators forms an abelian group under fusion. So in general, as we saw, the fusion rules is not a group, it's a ring. But suppose we assume that the fusion of line operators is a group. Then suppose that group is A, some abelian group, that such TQFTs we will call abelian TQFTs. The fusion is always abelian because we can always reorder the lines in 3 dimensions. So we just get an abelian group. Now for these TQFTs, correlation functions of arbitrary combinations of line operators are completely determined by what are known as topological twists. So if I take one of the line operators and do this, so this is some line operator, straightening it comes at the cost of a root of unity, and this is the topological twist. This is a root of unity. If this phase is 1, in the Chinese matter literature, we would call the anion that is for which this line is a Weyl line as a bosonic anion. If it's -1, it's a fermion. If it's a generic root of unity, we call it a generic anion. So this is the twist. What I mean by a twist. So for each line, we can specify a root of unity. And if we know the root of unity for each line, we can completely determine all the correlation functions of all configurations of line operators in abelian TQFT. So this is something that we will use. Another concept that we will use is that note that this group A that we define here is a group of topological line operators. So in this table, we can see it's 3D and we have lines. So it's a one-form symmetry of this TQFT. We can just phrase it as the one-form symmetry of this TQFT. And we can ask questions about, can we gauge the one-form symmetry? What happened? What is the anomaly for this one-form symmetry? And a subgroup of this full group A of line operators doesn't have any anomaly, it's non-anomalous if this twist is 1 on all the lines belonging to the subgroup. So this is also some fact that we will use. So if the topological twist is not 1 for a subgroup, then that subgroup cannot be gauged. So the anomaly is captured by these topological twists. So we will use these 2 facts in the next example. Any questions about this structure? Yeah. So now let us start with an explicit TQFT, abelian TQFT.
Sorry, just one question. So so this is like an anomaly between what? Between the one form symmetry with itself? Is that the statement?
Yeah, it's a self anomaly of the one form symmetry.
Okay.
Yeah. Back. Yeah. So suppose we have a 2+1D TQFT with 16 line operators. So I give you the spectrum of 16 line operators. The fusion of these line operators, so I'll call them LAB, where AB runs from 0 to 3. The fusion is just given by the Z4 times Z4 group. So we have an abelian TQFT. We have to choose a fusion group. We choose it to be Z4 times Z4. And that is this. And the fusion is given by Z4 times Z4 group multiplication. This is the explicit choice of the lines and their fusion. But to define the TQFT, we have to also say what these twists are. So I can give a function on this AB. So the twist is e to the 2 pi I AB over 4. So this is the twist for each of these line operators. And we can check that this data satisfies all the axioms for a 2+1D TQFT. So this is the abstract bootstrapped data that defines the TQFT. And we can ask, is this TQFT some kind of gauge theory? Or can we obtain this TQFT by gauging a symmetry of another TQFT? These are some questions we can ask, starting with this data. So,
sorry, just one question. So there is a constraint that this twist should also multiply. Is that constraint there? There's the theta AB, theta CD should be the theta of the right hand side.
So in general, I don't think the twist will multiply.
Okay.
It won't be like a character of the group.
Okay. Okay. So then is it true that I can? So that's a question I'm asking. Can I very independently give the twist, or is there some a priori constraint on this twist?
There are constraints. If you are abstractly defining this data, this twist has to be a non-degenerate quadratic function on the group. So that is the mathematical constraint that this function has to satisfy. So,
but there is no like it should not. It doesn't have any. It's just some general function.
Yeah, so requiring non-degeneracy and this quadratic form really constrains the functions that you can have. It's a small finite set of functions that you can choose for any given group.
Oh, you're saying it's a non-degenerate quadratic form?
It's a non-degenerate quadratic function, yeah.
Okay. Okay, thank you.
Because that is related to modularity of the TQFT. If you don't have non-degeneracy of the quadratic form, you will lose modularity.
Okay, thanks.
So I'm just starting with this explicit function here with the Z4 times Z4 fusion rules. And we can ask, is this TQFT, can it be described as gauging a symmetry of another TQFT? Can this another TQFT be the trivial TQFT? That is when we would call this TQFT a discrete gauge theory. Discrete gauge theories are TQFTs that are obtained by gauging a symmetry of the trivial TQFT. More generally, we can ask, can it be obtained by gauging a symmetry of another TQFT? So we know that suppose this TQFT can be obtained by gauging a symmetry of another TQFT, then we know that this TQFT must have some rep-G type one form symmetry. Why is that? If we have another TQFT and if we gauge some zero form symmetry of that TQFT, this theory must have Wilson lines for that group that we gauged. So there must be a set of line operators sitting inside this set of lines, which is the dual one form symmetry to the symmetry that we gauged. So this is similar to what is happening here, but in 3D. So we have to find a set of lines in this set of subset of lines in this full set, such that it is something like a rep-G structure, fusion rule. Also, we should be able to gauge that symmetry because, if you start with the theory and gauge symmetry, we have rep-G. If we gauge rep-G, we go back to the original theory. So this subset of lines that we find should be gaugeable. So that means once we identify a subset of lines, it should have trivial twist. We saw that is a condition for being able to gauge the rep-G. So let us look for lines in the set which are gaugeable. One choice is this L1, 0, for which we clearly have trivial twist, and it generates a Z4 one form symmetry. So the full fusion group is Z4 times Z4. We have a subgroup Z4 generated by L10, which has no anomaly, so we can gauge it. And if you gauge it, you will find the trivial TQFT if you go through the procedure of gauging it, which means that this TQFT is actually a Z4 zero form, Z4 Digraph-Witten theory. So this is Z4 Digraph-Witten theory written completely abstractly as a set of line operators and twists. But this choice of L10 is not unique. We can choose L20 and L02, again two line operators which do not have anomaly, but they generate a Z2 times Z2 one form symmetry, not Z4. If you gauge that, you will again get the trivial TQFT, which means that this TQFT is also a Z2 times Z2 Digraph-Witten theory. So Z4 Digraph-Witten theory and Z2 times Z2 Digraph-Witten theory are the same because it's the same, we get the same spectrum of line operators and topological twist. So when I say constructing the gauge group from the line operators, there is a choice of these bosonic lines that I have to make. And once I make a choice, we can construct a gauge group. But as this example illustrates, the gauge group is not unique and it depends on the choice of the line operators that you make.
Just one question. So when you're saying you're gauging these line operators, what, like abstractly from this data, do you mean just that, like you take a set of line operators, what you call bosonic line operators, and you project to the invariance of that under this product or something, or what do you do?
Yeah, so the action of the line operator. So can you see here? This part of
yes.
So if I have a line operator, so let me write it as. So if I have some line operator L, L1, L2, the action of L1 on L2 is given by the S matrix. So we have some. So a ratio of S matrices of the TQFT gives the action of L1 on L2. So if we have to make sure that these spaces, we have to take the set of line operators for which this action is trivial. So invariant under this action. Yeah.
So this action just leaves L2. Let's say if L1 is one of the things that you're gauging, then putting a linking with L1, we should give back L2. Is that
yeah, so this configuration should be equal to this phase times L2. Yeah.
Okay. So this factor should be 1. Is that what you require?
Yeah. So projecting to invariance means that this should be 1. So all the line operators for which this is 1, but when we do the gauging, we will find that there is only one line for which this is 1.
Right. Yeah. So hence you're saying it's a trivial.
Hence, I'm saying the resulting TQFT is trivial. Yes.
Okay. Thank you.
More questions. So this is the example that I would like to highlight to really understand what I mean by constructing gauge group from. And this is still abelian. So the reason why we could fix the gauge group by looking at the fusion in this case is because it's abelian. So we will get to non-abelian groups as well. But more questions on this? Okay. So with this example, let me go back to this question of getting group data from the character table. So let us list some of the properties of the group that we can determine from the character table. So if we know the character table, and if we sum over the first row of the character table, so if I label the rows by representations and columns by conjugacy classes, some classes, if I sum over the first row, then I will get the order of the group. This is how we can reconstruct the order of the group starting from the character table. I will just go through an explicit example of this in next slide. Normal subgroups can also be found by looking at the character table. You just look at a set of conjugacy classes for which the character value is the same as the dimension of the representation. Those conjugacy classes forms a normal subgroup. When I say we can determine the normal subgroup, I don't mean that we can determine what is that group up to isomorphism. I just mean that we can say what are the conjugacy classes which forms normal subgroups. That's all we can know from the character table. So then we can ask, can we reconstruct G up to isomorphism from the character table? And the answer is no. And there are well-known examples. The smallest order group which have the same character table but different groups is D8 and Q8. Distinct groups but the same character table. And the character table is the following. This is the character table for D8 and Q8. So here I have just some classes. Because we started with this notation for these groups, let me go back. So we have some generators for D8 in terms of RNS, generators for Q8 in terms of IJK. Because we started with this description, I'm just using those labels at the top. But if we are just looking at a character table abstractly, we won't have those labels. So these are the two. This is the character table, and it's exactly the same matrix. So there's no way we can distinguish between the two. So the question is, what data on top of the character table do we need to distinguish a group? Which is a question in group theory that people have studied a lot. So let us look at some data on top of the character table that we can use to determine the group. So we looked at Wilson lines and their fusion rules, but the fusion rules is not the only data associated with the Wilson lines. Wilson lines have associativity properties, crossing relations. So the crossing relations of Wilson lines are determined by these matrices. So this configuration of Wilson lines should be the same as this configuration of Wilson lines up to a matrix. So this matrix is acting on some Hilbert spaces, which I'm not saying explicitly here because we will not need it going forward. But just to highlight this, the crossing relations of the Wilson lines are captured by certain matrices, F matrices. And the braiding, if we have a braiding of Wilson lines, we can unbraid it at the cost of adding some R matrices. So this is some extra data that is also associated with Wilson lines. And it is known that N, F, and R together does determine the group up to isomorphism. So N, remember, is the fusion coefficients. The OP data is determined by N. F is the associativity, R is the braiding. This together does determine the group up to isomorphism. But F and R are different from N in the following way. N is the OP rules. Okay, maybe.
Just to remind me, N got you the character table as well.
Is N can be obtained completely from the character table. Yeah.
It's the other way around, right? You in the way we are proceeding, you first determine OP function and then get the character table.
That's right. Yeah. In the way we are proceeding, we have N, we can get the character. Yeah.
Also, if you in the previous slide you showed this character table for the two groups.
Mm-hmm.
Can you at least comment on the cardinality?
Yeah, sure. Yeah, so
the fact that they are the same cardinality also.
Yes, so in the character table, the cardinality of the group can be obtained by summing over so we have this unique row which has just positive entries here, which is telling us the dimension of the representations. You sum over this row, just take the squares of elements in this column and sum over that, and you get 8 in either. Yeah. So that is one way to get the cardinality of the full group.
If two different groups are the same character table, we are at least sure that or up to some rotation factor, we at least know that they are the same size.
Exactly. Yeah. We know that they have the same size. We know that they have the same number of conjugacy classes. We know that they have the same number of normal subgroups. There are a lot of data that we know that the groups should have in common. So yeah, so this data determines the group up to isomorphism, but F and R are basis dependent. What I mean by that is F and R depends, finding F and R depends on choosing certain basis elements in certain Hilbert spaces. They are not things that we can directly get from the lab, unlike N. The reason why I'm calling N more physical is because if you have these anions and you can braid them, you actually get this S matrix. If you know how to braid anions. From the S matrix, you can get N by the Verlinde formula. So N can be obtained if you know how to braid anions, and it's a gauge invariant quantity. F and R are not gauge invariant quantities. They depend on a basis choice. That is because these diagrams have junctions, and junctions involve a choice of local operators on the junction. That is why these are not gauge invariant. If you have an expression value for loops or links, they are gauge invariant. But whenever you have these junctions, this data is not gauge invariant. And it is not known what gauge invariant data is required to determine the group up to isomorphism of lines. So there should be some loop or link which gives you gauge invariant data, which should give you the group up to isomorphism. Because after all, this does determine the group up to isomorphism. But we don't know what that gauge invariant data is. We just know that this gauge dependent data gives the group up to isomorphism.
So I had a question. So this in Wilson lines, I understand roughly what you're saying by F and R. But if I just start with, finite group representation theory, what is F and R? N is some, as you said, it's very natural. But what is F and R from just the pure group theory point of view, without going into all this TQFT stuff?
Yeah, so I think for the pure group theory point of view, for finding F, for example, these are related to the 6J symbols, if that is more familiar.
Okay.
If you know the 6J symbols, you can find what F is.
And there's a similar kind of statement for R.
Yeah, for R, there's a statement. So if you start with,
right. Yes. Okay. I understand. Yeah. Okay. These are the six. Okay. Right. Yes, sorry.
Yeah. So this isomorphism of vector spaces on which the representations act give you R. Yeah.
Okay.
But finding these isomorphisms or 6J symbols, they are all very basis dependent quantities, and that's why I'm saying them as not physical compared to N.
But in the ring of representations, so there's a formal way to write these things, right? It's not like they're well-defined objects.
That's right. So if we lift the ring of representations to the symmetric category of representations.
Yes, in category of representation, yeah.
Yeah, then FNR is there in that category. So I'm just saying that category determines G up to isomorphism. Yeah.
Okay. So that is the statement that you're saying as a mathematical statement.
Yeah, that is already known. That is from 1991, Joyle and Street. Actually, Tanaka-Krein duality. So I'm just saying, if you're familiar with that, that is what I'm saying, that the symmetric category of representations determines the group up to isomorphism.
Yeah, so what is the statement that they are basis dependent?
Yeah, so their basis dependent is a statement that if we are finding, so in order to find these isomorphisms explicitly, we have to choose basis elements in these vector spaces. And it is not something like a link invariant, like the S matrix, which doesn't depend on a basis. This is a phase that you get, and it is not dependent on a basis. You have two links, and you get this link invariant. So these kinds of expression values of Wilson loops do not depend on a basis, so they are gauge invariant correlation functions compared to FNR, which are actually not something that you can get from the lab by braiding anions.
Okay, thank you.
Can I ask?
Yes.
Yeah. So the fact that these things are basis dependent, and this is not the gauge invariant data that can give you back the group. You're saying that, but that does not mean that there's some redundancy in the data, right? It's not to say something like that.
Yeah, I don't mean, yeah. So there is no redundancy in the sense that if you don't know R, still you cannot fix the group up to isomorphism. You need to know NFR in some basis completely to determine the group. But you can always change. So if I give you some data NFR and someone else gives you some data of NFR, it's very hard to compare them because you have to fix the basis first and then, because these are depending on lots of labels, which are all of the size of the order of the group. So if the order of the group goes high, even for D8 and Q8, for D8 and Q8, it is known how to compute them, but it's a lot of matrices to compute. Yeah. But I don't mean, so these are basis dependent. So if you change the basis, these do completely different.
Sure, but
yeah.
Computationally speaking, like suppose I choose all these bases, N everyone will agree on.
N everyone will agree. Yeah.
F and R will be different, but there's a procedure that will give me back the group from NFR.
Yes.
Without throwing away any of the data I have in my F and R.
That's right.
So, I mean, it's also necessary.
It's also necessary, yeah. Okay. We cannot get rid of any of this data. Yeah. Yeah, it's an if and only if correspondence between this data and the group.
Okay.
So
I have a naive question. It's a clarification actually. I mean, how do you write down the Wilson line for a finite dimensional group? Yeah, so I think it's yeah, I think we have to do something like lattice gauge theory, where we triangulate the manifold and then associate group elements to the edges and then sum over them.
So I'm not using, so in this, I will be more algebraic in this talk. I won't be using field theory language that much because it's finite groups. Yeah.
Yeah, but then what does the statement mean that these are not gauge invariant? Because I mean, there is no gauge field as such, right? I mean, so what does it mean that these are not gauge invariant?
That's right. So yeah, so gauge dependence is it's a name for the basis dependence that condensed matter physicists use. What I really mean in this context, without giving extra information, is that there are some bases that we have to choose on the Hilbert spaces associated with these vertices. And that is the dependence that I'm talking about. It is called a gauge dependence in the condensed matter literature. Because it's not something that we can, because these are dependent on a basis, we cannot get it from some link invariant. That's all I wanted to say.
So it's not gauge invariant in the sense of field theory, you're saying?
They may be related, but I'm not sure. They may be related. Yeah.
Okay.
Yeah. I think this FNR will change if we retriangulate the manifold in a different way. So that is not something that we expect to affect the gauge theory, right? The triangulation should not really, changing the triangulation should not change the gauge theory, the observables and the correlation functions. But this FNR are data that do depend on the way we triangulate the manifold when we compute discrete gauge theory data. So in that sense, they're, yeah.
In this crossover relation that you're writing, where does triangulation of the manifold come in? I mean, it is just a statement of Wilson lines joining and on either side, right? I mean, so I don't see where the triangulation of manifold comes in here.
Yes, that's right. Yeah. So yeah, I was actually talking about, so these kinds of networks comes in only if we are trying to gauge the symmetry implemented by these Wilson lines. I agree. So, you know, if we want to gauge the symmetry implemented by these Wilson lines, then we have to triangulate the manifold with these Wilson lines. And then there will be some configurations related by F. So in that process, the Fs will depend on that triangulation. But I agree that this is not the triangulation of obtaining this gauge theory itself. Yeah. But I think this basis dependence is related to what we mean by gauge dependence. But I would like to actually establish it. I'm not sure if I know the answer explicitly, how they're related. But in these diagrams, all I mean is there's a basis dependence. If we want to describe this isomorphism, we have to choose a basis. That's all I mean. Is that okay? Okay.
Yeah.
So yeah, so then the question is, because this FNR are hard to compute because they are basis dependent, the question is, can we add some gauge basis independent data to N so that we can determine G? So what is some other data that we can add to N so that we can determine G? But if you look at just Wilson lines, this is the data that Wilson lines tells us. So maybe it is better to look at some other operators that we have in the theory. And this is where surface operators will enter. So surface operators, I will describe a way of obtaining the surface operators. Before that, I would like to quickly describe a way of obtaining Wilson lines itself by gauging, because that will be very useful to understand how the surface operators appear. Suppose we have a TQFT, suppose we have a generic QFT T with G symmetry, non-anomalous. We can gauge it to get some QFT T mod G. But in the gauging procedure, we can add a 0 plus 1D TQFT. So just a line on which a TQFT lives. This TQFT is required to also have a G symmetry. And we can gauge the diagonal G symmetry to get a line operator in T mod G. So it's a usual gauging procedure, but we insert a 0 plus 1D TQFT, which also has a G symmetry. And instead of gauging the G symmetry of the T alone, we gauge the diagonal G symmetry of both. Then we get a line operator in T mod G. And the claim is that in this paper is that these line operators are precisely the Wilson lines that we know comes out by gauging. How do we see this? To see this, we have to actually know what does it mean to have this 0 plus 1D TQFT with G symmetry. So what is a 0 plus 1D TQFT? A 0 plus 1D TQFT is just a vector space, a quantum mechanical system with no Hamiltonian. So it's just a vector space. That's the data of a 0 plus 1D TQFT. What does it mean for this TQFT to have a G symmetry? It just means that this vector space is in a projective representation of G. Maybe generically a projective representation of G. That is just what we mean by a 0 plus 1D TQFT with a G symmetry. We should be able to gauge this G symmetry. So we don't want anomaly. Requiring this G symmetry to be non-anomalous means that it should actually be a linear representation. It should not be a projective representation. We should be a linear representation of G, which is the same data that labels Wilson lines. So at the level of labels, at least, there's more work to be done. But at the level of labels, we can see that inserting these kinds of TQFTs and gauging precisely gives you line operators which are again labeled by irreducible representations. So Wilson lines. But we can generalize this procedure. If we are doing this procedure in 3D, instead of inserting a line, we can insert a surface. So a 2D TQFT with G symmetry and gauge the diagonal G symmetry and carry along with this procedure. Now the resulting theory will have a surface operator instead of a line operator. So that is what we will do. So we start with the theory, we insert a G symmetric, now 1 plus 1D TQFT. We gauge the diagonal G, we now get a surface operator in the gauged theory. What are the surface operators? What are their OPEs is what we want to determine. So these surface operators exist in any gauge theory. So they are like Wilson lines. Now, whenever you gauge the G symmetry, you have these Wilson lines. And we have this particularly nice OP for Wilson lines given by representation theoretic data. Similarly, we have the surface operators whenever we gauge a G symmetry. What are the OPs for these surfaces? So to determine that, we have to know what do we mean by 1 plus 1D TQFTs. There's a completely explicit classification for these. And in a 1 plus 1D TQFT, we have local operators and line operators. That is the data that we have in a 1 plus 1D TQFT. It is known that local operators are determined by a Frobenius algebra. So, or the local operators, their OPE, their 2-point function, everything is determined by a Frobenius algebra. And the line operators are then determined by representations of those Frobenius algebras, or more precisely bimodules. So I'm just writing it here just to highlight that these are really well studied, because these are semi-simple TQFTs. We are not considering non-semi-simple TQFTs, they are more exotic. But they're also classified, but classification is not as simple as this. So we have this data. So the point is that we have topological local operators, topological line operators. This is a 1 plus 1D TQFT. What is a 1 plus 1D TQFT with a G symmetry? What does it mean for a TQFT to have a G symmetry? Line operators. So a TQFT has a G symmetry if there are line operators for every group element, such that the OP of those lines is the same as group multiplication. So remember, in 2D, a symmetry, a zero form symmetry is implemented by line operators. So saying that a TQFT has a G symmetry means in the set of lines you have, there should be a subset of lines which have the same OP as the group multiplication. So that is this requirement. But we also want to be able to gauge this symmetry. So we don't want any anomaly for the symmetry. Requiring that there should not be any anomaly is this network equality. So we recall this with an F symbol that we saw for the Wilson lines. Here we are saying that they are exactly the same. There is no F, which is saying that there is no anomaly. So when you eventually gauge the symmetry, you'll have to triangulate the manifold. And if you don't have this exact equality, the gauging procedure will depend on the triangulation. So the resulting theory is not well defined. So we have to require this so that this symmetry is non-anomalous. So this condition is for having a group-like symmetry. This condition is for having no anomaly. So let us solve this in a very simple case where the TQFT that we're interested in is the trivial TQFT. What do I mean by the trivial 2D TQFT? It only has one local operator. It only has one line operator. What does it mean for such a TQFT to have a G symmetry? And we can solve these constraints to actually classify them. So if we have a trivial TQFT, we only have a trivial local operator. We only have one line operator. All lines LG for all elements in the group is just mapped to one line. We only have one line in the theory. And solving this anomaly vanishing constraint here, all these lines are trivial. So there is no lines to fix. But these junctions, you can fix a complex number because these junctions are one-dimensional Hilbert spaces. So there is a complex number worth of data that you can fix in these junctions. So if you solve this for the trivial TQFT, each of these 4 junctions will just give you 4 faces. And that equality will require the phase to satisfy this equation. This is the condition for C to be a 2 cocycle. So in group cohomology, this is saying that C should be in the second group cohomology. So 1 plus 1D TQFTs with G symmetry are the same as choosing an element in the second group cohomology. So this is what I want to just highlight, that if we go through the procedure, we can actually classify 2-dimensional TQFTs with a G symmetry. And each of those TQFTs is a choice of insertion that we have when we do this gauging. And therefore, each of these choices is a resulting surface operator in the gauged theory. So this is a part of the data that defines the surface operators in the gauged theory. What is the general story? I won't prove this, but the general story is that there are 2 labels for this surface operators. We can choose a subgroup of the group, and for that subgroup, we have to choose a 2 cocycle. So this is the full data that labels those surface operators that we got by gauging, by inserting these surfaces and diagonal gauging. So those surface operators have 2 labels. One is a subgroup of the group that we started with. Another one is a 2 cocycle. So this is a set of surface operators that we have in the picture. These surface operators exist whenever we gauge a G symmetry. The resulting theory has these surface operators. So these are like the Wilson lines. Questions on this?
What do you exactly mean when you say that the junction carries a Hilbert space?
Yeah, I just mean that, yeah. Yeah, so if we have a line, then if you have a line L, then in general, there can be local operators on the line. And these local operators in general will form some Hilbert space. This is a Hilbert space of local operators on the line. If this line is trivial, then it is a set of local operators of the theory. So these are these non-genuine local operators because they live on a submanifold. So if you have a junction of lines, there can be some operator sitting here, local operator sitting here. Corresponding to these local operators, you can have, so if you have LA, LB, LC forming a junction, you can have certain Hilbert spaces associated with local operators sitting on this point. And these are known as fusion spaces. So these can be higher dimensional in general, but when LA, LB, LC are all group-like, this is one-dimensional. So when you solve this constraint, you have to choose a basis element in this one-dimensional Hilbert space, which is a choice of a complex number.
Yeah. So for instance, if you take the line, say LK, for instance, on your left of the equality, so that corresponds to some charge at one end and another charge at some other end, or rather one group element at one end and another group element at the other end, right?
Yes.
That's the Wilson line, right?
Yes.
So now you're saying that, I mean, and for instance, this LGK middle line, that would simply correspond, what would that correspond to in this picture?
Yeah, so LG, LK, LGK are the 3 so these are not really Wilson lines because we haven't gauged the theory yet. These are some line operators labeled by group elements implementing the symmetry. That is what we mean by having a G zero form symmetry. And those lines can have junctions. And the junction of LG, LK, and LGK can have a local operator living there. But the set of options, this is a one-dimensional Hilbert space worth of local operators. So to fix that, we have to choose a complex number. So in the language of representation theory, I can tell you what this is. So if we have 3 Wilson lines forming a junction, So if we have three Wilson lines L, R1, L, R2, L, R1 times R2 forming a junction, then this point local operator here is the intertwiner between this product. So let me call this actually R1, R2, R3. So R1 times R2 to R3. So the different maps between this representation and this representation gives you some space of maps. That will be this, what the possibilities that we have at this junction. So the
intertwiner comes from the braiding. I mean, you can possibly, I mean, the example that you had previously, that braiding corresponds to, this braiding complex number that you had. I mean, this thetas, for instance.
Yeah.
Right.
Mm-hmm.
So those thetas are those the complex numbers that you're talking about? No.
No, they are not the ones, because that comes from the fact that there is a braiding between these lines and we unfold it. There's an extra complex number dependence that I suppressed in those diagrams because there are already many indices. But in all of those diagrams where we have a junction, there's an extra label, which is a choice of a basis element at the junction. But here the junction is very important, so I wrote it down explicitly. Yeah. So the R matrices, the F matrices, everything, in all of those diagrams, we have to actually choose basis elements at each of those junctions. So there are more labels than what I wrote down.
Okay.
Yeah. So to summarize, what I want to say here is that we can actually insert these surface operators when we do gauging, these 2D TQFTs when we do gauging, and these leads to surface operators in the resulting theory. And we can actually classify them in the sense that we know that if we start with the group G, subgroups and second cohomology elements is what classifies these surfaces. But for Wilson lines, we have a representation theory explanation for why, we have this labeled by representations. Here we have this label subgroup and a cocycle. Is this related to some kind of representation theory? So are surfaces also labeled by some representations of the group? And the answer is that yes, they are. And I will very quickly go through that, because that description allows us to actually compute the OPE. So far we haven't computed the OPE, we just wrote down the list of surface operators. So for that, I had to introduce these two vectors and two matrices. So these are like vectors and matrices that we know and love, but there's a slight complication that a two vector is a vector of vector spaces. It's not a vector of numbers, it's a vector of vector spaces. Okay. And a two matrix is a matrix in which every component is a vector space. And there is an action. The action of a two matrix on a two vector is just given by tensor product and direct sum. So wherever you see plus and multiplication, you replace it by tensor product and direct sums. And this action may look a bit weird, like what does it mean to have these kinds of actions? But these actually appear a lot even in Chern-Simons series. And the way they appear is in the following way. So suppose you have two line operators, L1 and L2, permuted with each other under some symmetry. So there is a zero form symmetry which permutes these lines. But as I said earlier, each of these lines in general can have some local operators sitting on them. So the Hilbert space of local operators of L1 sitting on L1, I will call it HL1. And the Hilbert space of local operators sitting on L2, I will call it HL2. So this action, which is permuting these lines, is actually permuting two Hilbert spaces, if you take into account local operators living on lines. So these kinds of permutation of Hilbert spaces actually do occur in theories we're interested in. And that is a kind of action that we want. Even though this looks very generic, we will see that it's just permutations at the end of the day. And this is the kind of actions that we are interested in. And once we define these two matrices, we can define two representations. So now everything we add in two to it. So what are two representations? We start with a group. For every group element, we fix a two matrix. So we don't fix a matrix, which will be normal representation theory. For every group element, we fix a matrix, a two matrix. Now we require these isomorphisms. For normal representations, we require that G times H is GH. which is the homomorphism condition, right? But now this rho G, rho H, rho GH are two matrices. It doesn't make sense to equate them because they are vector spaces. You have to define isomorphisms between these objects. That's some extra data that you have to specify. So defining two representations mean finding maps from the group elements to two matrices such that you also have these maps, imposing a homomorphism condition at the level of these maps. So when this is a higher version of representation theory, and whenever you do this higher categorical things, you replace equalities with isomorphisms. So this is one example of that happening. And you also require that the trivial element of the group is mapped to the trivial, this should be a row. And the trivial element of the group should be isomorphic to the trivial 2 matrix. The trivial 2 matrix is just like the identity matrix, but the diagonal ones are one-dimensional Hilbert spaces. Everything else is a zero-dimensional Hilbert space. So that's the trivial 2 matrix. This is the data, but there are some constraints on it. We start with this product of 2 matrices, and we can do this phi operation on these two. We get this product. We can again do a phi, we get rho GHK. But we can do the other way around, and these two should agree. So there's a compatibility condition that we impose on this extra structure. We can solve all this. I won't solve all this here. We can solve all this. And what we find is exactly the same that we found before. That is, two representations, irreducible two representations are classified by subgroups of the group and two cocycles, which is exactly the same set of data that we found when we were describing the surface operators by gauging. So line operators, Wilson line operators are labeled by one representations or normal representation theory. These kinds of surface operators are labeled by two representations. And this is where representation theory is still in the picture. And like OPE of Wilson lines come from tensor product of one representations, OPE of the surface operators come from tensor product of two representations. So if we know how to take tensor products of these representations and decompose them into irreducibles, we know how to take OPE of the surfaces. I mean, this requires proving that the surface operator fusion is same as this. That has been done. So the point is that the fusion of these OPEs, so fusion of the surface operators, also have a representation theoretic origin. And we can actually explicitly write down what the fusion is. So if we have two surfaces, we can bring them together parallelly. And the fusion of two surfaces gives you a sum of surfaces depending on some data. So let me write it down as an equation. So if we have two surfaces labeled by subgroups K and H, again, depending on some two cocycles C and D, the fusion or the OPE is a sum of surfaces labeled by this subgroup and this two cocycle. So this is the OPE for the surfaces, which we can completely explicitly write down. This is actually simpler than doing one representation theory, because for normal representations, we cannot actually write down a very simple expression like this for tensor product. Well, we can write down in terms of characters, but here it's directly in terms of subgroups and cocycles. So with this, what do we need to do? We have this, suppose we know the OPE for surfaces. The question is, what information about the group can we learn from these OPEs? We repeat the same procedure as we did for lines, but now for surfaces. So these surfaces form a semi-ring again, which is some 2 rep G. This is a ring of surfaces. So let me go to an example directly where we can see all the different fusion rules. Suppose the gauge group that we start with is Z6. If we gauge a Z6 symmetry, we have 6 line operators, Wilson lines, which again form the group Z6 under fusion. We can also enumerate all the surface operators in a Z6 gauge theory. And the surface operators are labeled by subgroups and two cocycles, but the two cocycles are all trivial in this case. So all you have is subgroups. So you have 1, 2, 3, 4 surface operators, and their fusion and their OPE or fusion rule is given by these data here.
Can I ask you? So we understood how to describe a Wilson line with a discrete gauge group.
Mm-hmm.
How do I do a similar construction for a surface operator? Just look at plaquettes or?
I think it should be that, but I don't think it has been worked out yet. I only know a description of this in terms completely algebraically. I don't know Yeah, like for example, I wonder if there is an expression for these surfaces like Wilson lines, but instead of taking a representation label, you take a two representation label, and there is some traces on a two representations that you can do to define gauge invariant objects. So to find some nice closed form solution expression, but I'm not sure. Yeah.
I was just having in mind Stokes theorem, you know.
So
most probably that's not the answer.
Yeah, I'm not sure.
In non-abelian Stokes theorem,
Mm-hmm.
can actually do it.
Right.
Is it that? That's a surface operator.
Yeah.
Okay. Now, but maybe that's not what you're talking about.
Yeah, I don't. So these surface operators also have, and you can have configurations where these surface operators do have end lines, which are Wilson lines, you know. So maybe they are related to Stokes in some ways, but I'm not sure if, yeah, all the details are correct. Yeah.
Interesting.
Yeah, definitely. Yeah. Yes. So with these examples, let me highlight that this particular fusion rule. So whenever we gauge this group, there's always this special surface which is labeled by the trivial subgroup and the trivial cocycle. There's a unique surface existing in any gauge theory. And if you take a fusion of that with itself, you will get 6 copies of itself. And the 6 is the order of the group. So in this example, okay. Similarly, we can look at this fusion here. You take this fusion of Z1, 1 with Z2, 1. The answer is order of the group divided by the order of the group here. Another observation. Yet another observation is this particular fusion here. Z6 is a direct product of Z2 and Z3. So if you take a fusion of these two surfaces labeled by Z2 and Z3, the outcome is Z1. And there's only a unique outcome. All of these cases, you had multiple surface operators appearing. This is the unique surface operator appearing in the fusion. So this is like a group multiplication in some sense, at the level of just this fusion. So this is kind of capturing the fact that this group is a direct product of Z2 and Z3. We can repeat the same thing for another example, which is S3. We can enumerate the subgroups.
Sorry, just a question. So I think you told this already. The subgroups are the unbroken groups in some sense. After the surface operators break the group into the subgroup. Is that how you should think about it? The subgroup that labels the surface operator is the unbroken group.
That's right. Yeah.
Okay. Yeah. Just making sure. Okay. So you're saying that if you have a surface operator which leaves this subgroup invariant, then okay. And then you kind of fuse such surfaces. What are the possibilities that can happen? Is that
that's right? Yeah, exactly.
Okay. Thanks.
So if we have to fix a starting point, and if the starting point is that we know these fusions, what can we know about the group? And we saw some observations that we know the order of the group in this case, order of some subgroups, and order of the fact that it's a direct product. We can do another example of S3. Let me quickly say that we have these subgroups Z1, Z2, Z3. There are many subgroups of order 2 in S3, and there are 2 subgroups of order 3. One subgroup of order 3. But I'm just writing it like this because these surface operators only depend on conjugacy classes of subgroups. This is a subtlety that I didn't explain, but each subgroup doesn't define a distinct surface. Only conjugacy classes of subgroups define distinct surfaces. So here there are only 3 conjugacy classes of subgroups except for S3 in S3. And all of them again have trivial cocycle. We just fuse them. Find the surface operator fusion in S3 gauge theory, and this is what we get. Again, we can observe something. Again, we see the order of the group sitting here. Again, we see that there is when we fuse these two, Z2 times Z2, now we get a sum of things. Note that Z2 in S3, any of the Z2s that we take in S3 is not a normal subgroup. And whenever you take surfaces which is not a normal subgroup, you actually get a sum of distinct surface operators. In the Z6 case, we only had one type of surfaces coming out, even though there were multiple copies of it, because in Z6, all subgroups are normal. In this case, we have a non-normal subgroup, so we have this kind of fusion rule. Again, we observe that we have this kind of fusion here, Z2 and Z3 giving Z1, which is capturing the fact that S3 is a semi-direct product of Z2 and Z3. We can generalize all of these observations in a generic situation and say that in general, the fusion of this special surface always has the order of the group coming out in any gauge theory. Order of subgroups can be found. So if we fuse this SK1 with SZ11, you get this order of the group divided by the order of the subgroup. The crucial thing here is that this subgroup is not required to be normal. So this fusion also knows about non-normal subgroups, which you cannot find from the character table. That's the thing. You know more other things that the character table doesn't know. Also, normal subgroups can be identified, which you can also do from character table, but you can also do it from surface operators. If K is a normal subgroup, if it satisfies a fusion rule of this type, you can prove this using the expression for the fusion rules. And also you can find the second cohomology group of the group. So there are many, many properties of the group that you cannot find from the character table that you can find from these. One thing that I want to highlight is that this surface operator fusion can actually distinguish between when a group is a direct product, semi-direct product, or a extension, which is again something that you cannot do from character table. And that is precisely why you can distinguish between D8 and Q8, the examples that we started with, using surfaces, but you cannot distinguish them at the level of character tables. So this is why surfaces know more. So I'm sorry about going over time. Let me quickly say one more thing about these surface operators. We can ask, are there gauge theories or gauge groups for which we get exactly the same set of surface operators and exactly the same set of fusion rules for surface operators? So D8 and Q8 were examples where we had the same fusion for lines. We can ask the same thing for surfaces. And in order to find such examples, I had to just look at some properties. I have to prove certain things like two gauge groups have isomorphic surface operator fusion. If the groups have the same thing called this Burnside ring, maybe you're familiar with it. So you can actually use the literature on Burnside rings to find examples. So let me go to the example to conclude. So these two groups, which are very, very high order groups, have the same surface operator fusion. So what this shows is that surface operator fusion alone cannot fix the gauge group, because there's a counterexample to it. But these two groups can be distinguished using their character table. So Wilson lines do distinguish these two groups, even though surface operators do not, which means Wilson lines know about properties of the group that surfaces do not, and surfaces knows about properties of the group that Wilson lines do not. We can combine both to distinguish many, many groups. So let me conclude by saying that there are various properties of the group that can be deduced from lines and surfaces. There are Wilson lines know about normal subgroups, but surface operators also know about non-normal subgroups, and that is really where we can use surface operators to distinguish many groups that Wilson lines cannot. The properties of the group that can be found from Wilson lines cannot be found from surface operators, some of them, and vice versa. And the natural question is there an integer n? So we have only gone till surface operators. Is there an integer n such that fusion rules of operators of dimension less than or equal to n fixes the group up to isomorphism? So surfaces we know is not the answer. So can we go to membranes? In 4D, we can go to membrane operators, look at their fusions. They will presumably be labeled by 3 representations, but 3 representations have not been completely classified. Still working, work is going on in different mathematical communities on it. But once we know that, we can ask this question. There is some indirect reason why 3 may be the answer, but I will keep that to the discussions. Thank you very much.
Yeah, it looks like I thought you wanted to say that we ought to use them in conjunction. The fusion rules of lines and surface operators in conjunction give us a lot more than any individual class.
That's right, yeah.
So is the last line supposed to be like up until what n is required, like all of them, or just at n?
Probably all of them, n and below. I think maybe surfaces and lines together may not be enough. Even though I actually don't have an example where both surface operator fusion and line operator fusion are the same. There are some candidates, but they have so many surfaces that it's not possible to do it by hand. So I have to find some program to compare them. Yeah.
But the indirect evidence for n equals 3 is you're saying like basically line surfaces and hypersurfaces of n equals 3 will do.
Yeah, so line surfaces and membranes might be enough, and the indirect evidence is quite indirect in the sense that it comes from a result on Frobenius characters. The Frobenius defined these higher characters, which are not directly related to these representations that we talked about. And there is a mathematical result which says that a group is determined up to isomorphism if you know the 3 characters. Now, if 3 characters can be determined from 3 representations, which presumably may define these membranes, that may be a way to prove this, but it's a very indirect evidence. Yeah.
Can I understand this as a like earlier you said that if we had that NFR in some cases, we can determine the groups by some.
Okay.
So, in some sense, knowing these surface operator fusion rules and let's say if n equals 3 is actually doing this, knowing the membrane fusion rules is sufficient to determine the group. Is it like the NFR being encoded in these fusion rules in a complicated way, or like what's the search exactly I'm trying to figure out?
Yeah, so if membranes are enough, then NFR should be in the membrane fusion encoded in it. So there's lots of sets of integers that the membrane fusion will determine. And those integers somehow knows about surface fusion and line fusion. So those NFRs should be in there if it is true. Yeah.
And fusion rules are basis independent, right?
They are basis independent because once we fix the set of, so we have to fix a set of operators which do not decompose into a sum. So we are fixing some simple operators. If we fix that set, then they are basis independent. We just get some integers. Yeah.
Is there a question online?
Hi, I have a question. Thanks for the nice talk. So at least in these cases, in these lower order cases, it seems like the surface operators and Wilson lines are alone enough to determine the group up to isomorphism. So in these cases, how does the NFR coefficients manifest themselves in the fusion rules of surface operators? Do we know that?
Yes, I think there are some cases where I know how to. So there are some functions you can define using the fusion coefficients for surfaces, which will give you the characters of the group, the normal characters of the group, which will then give you the fusion coefficients for lines. But I don't know a general expression. I only know it for some class of groups.
What about F and R then? Can we get those from the surface operators?
Yeah, in those cases, it should be possible to get FNR from surface operators, yes. If we can fix the group, yes, we should be able to get FNR also. But yeah, FNR, for even if we know the group multiplication, finding FNR is not easy. So from surfaces, we can find the group multiplication table. And that, at least that direction is very hard. But I don't know if there's a way to find them directly. Maybe it will be interesting if there's a way.
Okay, thanks for that.
Any more questions? If not, then let's thank the speaker.
Okay, thank you. Yeah.